Hello, everyone. Welcome to Compass Seminar Friday. My name is Payson Tan, fifth-year PhD student, sadly, already in University of Miami. And today, our speaker will be Dr. Lichuan Wu from Sweden. Here's some background information about Lichuan. He obtained his bachelor and master in engineering from Wuhan University of Technology from China, and his PhD in meteorology from Uppsala University in Sweden, and a postdoc in Swedish Meteorological and Hydrological Institute, Norrköping, Sweden. Now he's an associate professor at Uppsala University, and Lichuan's research focus on the air-wave-sea interactions, coupled model development, and polar extreme events. In his free time, he likes to go swimming and cooking. And today, Lichuan will give us a 45 seminar on special session Compass Friday. So Lichuan, please take the stage. Thank you.
Thank you. Can you see my screen? Okay. Thanks, Payson, for the introduction, and thanks everyone for joining this talk. So I'm Lichuan from Uppsala University, and today I will talk about the development of polar lows in future climate scenarios over the Barents Sea. So this study was done together with one of my PhD students, and also together with Professor Anna Rutgerson. And this satellite image shown here is one example of the polar low. And from the satellite image, you can see that this polar low has quite similar structure with tropic cyclones in terms of the cloud structure. So for those who are not familiar with polar low, and polar low is a small but fairly intensive maritime cyclone, and which was generated in the polar world of the main baroclinic zone, can be the polar front or the other major baroclinic zones. So since polar low is mesoscale system, and the size of the polar low is much smaller compared to the mid-latitude cyclones and tropic cyclones, and the size is commonly between 150 to 600 kilometer, and it's happened over the open water, and the near surface wind is larger than 15 meters per second. The lifetime is much shorter compared to the tropic cyclone. It's only between 6 hours to 36 hours. So because of the smaller size and short lifetime, it's a challenge for the weather prediction model to accurately capture the polar low and predict its intensification of the polar lows. Meanwhile, the climate model has relatively low resolution. It cannot capture the polar low at a relatively smaller size, which may be a possible reason why we have the large uncertainties for the climate model in the polar regions. So the generation mechanisms of polar low has many different, it's depend on the case by case. So there are several different mechanisms which are used to describe the intensification of the polar low. One is the classic mechanisms which used to describe the generation of the mid-latitude cyclones, and the generation mechanisms for the tropic cyclones also used to describe the intensification of the polar lows, such as the conditional instability of the second kind and wind-induced surface heat exchange. Here, I will not go to detail about the generation mechanisms. And why do we care about polar lows? Because the polar low can produce the high wind and also sometimes the monster waves, which can make significant damage to the ships and to the offshore infrastructure. And also when the polar low landing, it can produce very extreme snowfalls just in a few hours. The accumulated snow depths can be more than 1 meter. And with global warming, the ice is decreasing in the Arctic every year, and there's open another potential for the Arctic shaping roles. So with those shapes, and we need to have better understand about the distribution of the polar lows and also their the extreme wind or the snowfalls linked to the polar lows. Even though the polar lows, the scale of the polar low is quite small, it's only 150 to 600 kilometers, but it's definitely can have significant impact on the large scale circulations. There's one study and try to investigate the polar law impact on the large scale ocean circulations. And with polar law and without polar law, and they found that the polar law can increase the volume of the southward transport of the Denmark Strait overflow water, and also spin up the entire North Atlantic subpolar gear, and also enhance the northward heat transport. So based on those backgrounds or motivation, we have three motivations for this study. And the first one is that the climate model has lower resolution to capture the polar law, then we need kind of the high resolution model to investigate about the climate impact on the polar law. And also the polar law has significant impact on the coastal community in the high latitude. And we need to better understand about the extreme weathers associated with polar lows, and also to better understand the change of polar low in the future climate in terms of their intensity and their frequency and etc. So the aim of this study is to investigate the development of polar low in future climate scenarios, and we choose two different scenarios. One is this SSP2 and one is SSP3. So this is general information about the climate change signal in these two different climate scenarios. And the left panel is for the SSP2, the 4.5 scenario, and the right panel is for the SSP3, 7 this scenario. The color represents the SST change in the end of 21st century, and the yellow contours represent the air temperature change at 850 hectopascal, and the change of the sea ice is represented by the dashed green lines. So we can see that the sea surface temperature will increase about up to 5 degrees in this SSP2 scenario, and for this scenario, it will increase up to 8 degrees. But for the air temperature, and it's increased more in this area. But for the ice-covered area, the air temperature increase less than the sea surface temperature increase. So what we did is that we used the WRF model and to design several sensitivity experiments. And in the control experiment, it's kind of the current climate situation. We use ERA5 to provide the initial and boundary forcing for the WRF model. And for the climate scenario, and we use the pseudo-global warming method to introduce the warming signal to the initial and boundary condition. So the parameter that introduced include the temperature and different height and the sea ice concentration, and also the sea surface temperature and humidity. Because here I didn't list the humidity because in the WRF model, we use the relative humidity. When we compared the relative humidity in the current climate and the future climate condition, that doesn't change much. But if we calculate the specific humidity, definitely the specific humidity in the future climate will increase. So we put the difference between the future climate and the current climate into the initial and boundary condition. Since the different climate model has different performance, and then we use 10 different CMAP climate prediction results and done 10 ensemble member simulations. this plot shows the model domain that we choose. And we choose two polar laws for the simulation, and we use polar law A represents the polar law that happened in 2010, which is very strong polar law, and polar law B is in 2011 in January, and is also strong, but is weaker compared to the polar law A. So this upper panel show the situation of polar law A, and bottom panel show the situation of polar law B. The color represents the temperature at 500 hectopascal, and the contour show the geopotential height, and this right curve show the track of the polar law. And we can see that for the polar law A, it has a strong this cold trough here, represent a very strong marine cold air outbreak. For the polar law B, it's a relative meander of the cold air outbreak. But these two polar law represent the typical polar law in this area. One is kind of moving in the east, one is moving into the southeast. That's why we choose these two polar laws to represent the general situation of the polar laws in this area. So firstly, we look at the track of the polar law, and the black curve show the polar law in the current climate situation, and the orange one here represents the polar law track in the climate scenario 4.5, and the blue curve here show for the results in the climate scenario 4.0. The up panel show the polar law A, bottom panel show polar law B. And the relative thin line is from the different simulation when we introduce the different CMAP 6 global warming signal. And the thick line here is represent the ensemble mean. So we can see that the polar law in the future climate will shift a little bit south. It's a little bit different with what we expected. Then we try to investigate the reason why the polar law in the future climate will move a little bit south instead of in the north. Then we check the large-scale background wind condition, and we found that in the future climate, and the future climate signal will introduce kind of the background wind shift a little bit south. That's why the polar law moved a little bit, the track for polar law moved a little bit south, because the track of the cyclone is largely dominated by the large scale wind condition. For the intensity of the polar law, and here the left panel show the minimal sea level pressure, and the right panel show the maximal surface wind speed. And similar with the previous slide, up panel is polar law A, bottom panel is the polar law B. We can see that the black curve show the the default simulation, and the blue curve is for the climate scenario 4.5, and the right curve show the simulation in the climate scenario 7.0, and the shadow show the different CMIP members. What we can see is that the intensity of polar law in the warming climate will be much weaker compared to the current climate situation, but it's more significant in the minimal sea level pressure, but for the wind speed is much relative scattered, but the general pattern is it will become weaker in the future climate. And then we want to know what is the reason why the polar law intensity is weaker, and then we investigate 4 different parameters to quantify which is the mechanisms that leading to the weaker polar law. The first mechanism is the baroclinic instability, and which is very important for the initial polar law development. And second one is the atmosphere static stability, because it will affect the convection of the atmosphere during the polar law development, and also it will impact the energy conservation through the baroclinic instability mechanisms. And also surface heat fluxes will be important for the polar law development, because it supply the energy to the atmosphere, and also the latent heat releasing, because it's introduced the atmosphere destabilization. Then we investigate these four different parameters to check what will be happening in the future climate. First of all is the baroclinic instability, and we use the eddy growth rate, and which kind of represent the baroclinic instability. And in the future climate, we can clearly see that this is just one snapshot from the ensemble mean of different climate scenario. We can see that in the future climate, the baroclinic instability will decrease significantly, and importantly for this region, which represents the cold air outbreak region, and for the center of polar law is also slightly decreased for the polar law A, and for the polar law B, and the baroclinic instability around the center of polar law is decreased significantly. Then we try to see the time evolution of the baroclinic instability around the polar law center, and then we plot the time series of the average baroclinic instability of the area average. Then we see that with global warming, the baroclinic instability is decreased, similar as we showed in the spatial distribution. And polar B is similar, but in polar A, we see increase of the baroclinic instability in the surface, near the surface. Then we investigated what the reason behind that. Then we found that it's because this polar law approaching to this land area, and in this area, in the current climate, is covered by the ice, but in the future climate, the ice will partly melt it. That's why it's kind of, in this area, there's more heat fluxes compared to the current climate. This enhanced heat fluxes will trigger this baroclinic instability, increased baroclinic instability in this area. When we do the average around the polar center, that's why we see the intensification of the polar law near the surface in this plot. But it doesn't impact on the intensity of polar law, because after the hour around 30, the polar law is in the decay stage. Then the baroclinic instability is not the key factor here. So in general, the baroclinic instability is reduced with the warming climate, which means that the future climate scenario is not favorable for the polar law intensification in terms of the baroclinic instability. Then the second factor is the atmosphere static stability, and then we use the marine cold air outbreak index to quantify the atmosphere static stability, which is defined as the temperature difference between the surface and the temperature at 850 hectopascal. For the future climate, we can see that the marine cold air outbreak index is significantly reduced. That is mainly because in the Arctic area, the temperature increase is much faster than the sea surface temperature increase, which means that the icy temperature difference will be decreased. Then the atmosphere static stability will increase. Then we also check the surface heat fluxes. And this is for the polar law A, and the upper panel show the sensible heat fluxes, and the middle panel show the latent heat fluxes, and the bottom panel show the precipitation. As we expected, the sensible heat flux will be reduced. This is because the air temperature increased much faster than the sea surface temperature reduced the air-sea temperature difference, leading to the reduction of the surface heat fluxes, surface sensible heat fluxes. For the surface latent heat fluxes is increased, generally is increased. This is mainly because the air temperature is become warmer, it can hold more moisture, leading to the surface latent heat flux increased. Similar for the polar law B, and we found the similar pattern. But interesting here, we found that in the future climate, even so, the intensity of the polar law is decreased, but the precipitation is increased, which means that the snowfall becomes even kind of dangerous things for the coastal community in the high latitude. We also check the latent heat resisting, which is related to the microphysics processes in the model. Similar, we found that the latent heat resisting in the future climate will increase, but here for the polar A, this have some decreased pattern compared to the control experiment. That is also because the ice melting in the dissipating stage of the polar law. So a little bit summary about why the polar law intensity is decreasing in future climate. That is because the baroclinic instability is reduced, which kind of implies the development of polar law, and the atmosphere static stability is increased, and also the total heat flux is reduced, even though the sensible heat flux is increased, but the latent heat flux is increased. And then the latent heat resisting is increased, and this process is kind of can enhance the development of polar law. But when we combine the 4 different processes, the polar law intensity is decreased, but the precipitation is increased. This is because the latent heat releasing is increased. And what about larger scale? Because now this 2 polar law cases is focusing on is over the Barents Sea, because the polar law can happen in the normally in all these regions over higher than 60 degree latitude. This plot just show the polar law track intensity in the north hemisphere. The popular area of the polar law is definitely in the Nordic Sea area. Then we try to see, investigate what will happen in the other area. Then we plot this 3 parameter that's mainly controlling the polar law development. One is the marine cold air outbreak index, which represents the atmospheric static stability. The upper panel show the current climate simulation, and the bottom panel show the difference between the future climate and the current climate. We can see that in the future climate, the atmosphere becomes more stable particularly in the Nordic Ocean, but in the ice-covered area, the atmosphere becomes more unstable. That is because ice starting melt. And for the baroclinic instability, we still use the ED growth rate, and we see that in the future climate, the baroclinic instability in the Nordic Sea area is decreased significantly, but for the other polar law generation areas doesn't have significantly decreased. For the surface heat fluxes in the future climate, the surface fluxes will reduce in the Nordic Sea Ocean, but in the other area it will increase. Based on this, we can kind of expected that the polar law intensity will decrease in generally in the North Hemisphere, but the decrease of the intensity in the Nordic Sea will be much significant compared to the other area based on this analysis of this 3 parameter. And the sea ice retreating region might be the new place for the polar law for the polar law generation. And in this study, in the previous simulation, we used the standalone WRF model, but we also found that the atmosphere-ocean coupling probably can have significant impact on the polar law intensity. Then we use the coupling model to investigate if the coupling processes can have significant impact on the polar law or not. Then we designed this 3 experiments. One is only coupled with the atmosphere, with the wave model. It's kind of change the reference length. And the second experiment is kind of only the atmosphere coupling with the ocean model, kind of operated SST every 15 minutes. And the third experiment is kind of the atmosphere, ocean, and ice coupled together. And the wave induced mixing in the ocean also include, and the wave impact on ice also include in the fully coupled model. Then we use the polar A as example to check if the coupling have impact on the intensity or not. So this is the simulation results in terms of the minimal sea level pressure. The black curve shows the control simulation. When we add the atmosphere wave coupling, and the polar law is become weaker. And when we add the atmosphere ocean coupling, the polar law becomes stronger. Then it's a little bit different with what we expected, because we are expecting that the RC coupling processes will reduce the sea surface temperature, then kind of reduce the heat fluxes, surface heat fluxes. Then it can weaken the polar law, but the result is opposite as we expected. Then we have a hypothesis. That is because in the polar region, the temperature inversion is commonly observed. Then there will be 2 different scenarios. When without the temperature inversion in the ocean, the mixing processes kind of decrease the sea surface temperature. This is kind of the solid line here represent the initial sea surface temperature. And when the polar low passing, the strong wind and the high wave will mix in the upper ocean and bring the cold water to the surface. That's why the sea surface temperature will reduce. Then it will weaken the polar low. But when there are temperature inversion, this is the initial temperature profile. And for when we have temperature inversion, when the polar low passing by, the strong wind will enhance the mixing and bring the relatively warmer water into the surface, then increase the sea surface temperature. Then it will enhance the surface fluxes, then leading to the intensification of the polar law. Based on simulation, and we found that there are temperature inversion in the during the polar law development. And also we found that when we adding the wave-induced mixing in the upper ocean, this kind of temperature warming in the sea surface will be much stronger. Here just to show one point with time evolution. Then we want to know if this is just the model results, or in the real situation it happened. And then we found 2 satellite image, and this is the satellite image for the sea surface temperature before the polar low, and this is from our model simulation of the sea surface temperature. And this is different of the satellite sea surface temperature. The day after the polar low minus the day before polar low, we see that the sea surface temperature is increased up to more than 1 degree. And also, we also see the similar pattern in our simulation. Then we can confirm that it's not only the simulation results, it's also captured by the satellite images. So the summary about this study is that with the climate warming, the intensity of the polar low decreased, but the precipitation associated with the polar low will increase. The decrease of the polar low intensity is because the baroclinic instability reduced, the atmosphere becomes more stable, and surface heat flux is reduced. The precipitation increases because the latent heat releasing is increased. And also the intensity of the polar low will reduce in the North Hemisphere in general, but the reduction of the intensity will be more significant in the Nordic Sea region. The air sea coupling can enhance the polar low when there's a shallow temperature inversion in the ocean. But here we only use one polar low case for this study. More studies should be done to investigate what will happen of the air sea coupling in the future climate and how it impacts on the intensity of the polar low in the future climate. That's the study that's doing by the PhD student. That's the main thing that the content that I want to deliver. If you have any questions or comments, I'm very happy to discuss with you.
Pause.
Thank you.
Thank you, Lichuan, for the great seminar. Does anyone in person have any questions? Akita.
Go with the microphone.
Thanks. Do I need to do anything? Okay. Much enjoyed your talk. My name's Makita Zaidam. I also want to mention that myself and my student, Sam Ephraim, who's also in this room, we're going to Kiruna in a month to do a field campaign on colder outbreaks over the Norwegian Sea with your colleagues, Michael Chenstrom and Gunilla Svensson.
Mm-hmm.
So much appreciated getting to hear about this. But my question is that I've also seen literature that suggests that colder outbreaks could increase in the future because of weakening of the jet stream, allowing easier southward transport of polar air. And I wondered what you thought of that.
Yes, definitely the cold air outbreak is not another topic. With this study, we are focusing on the when the polar low generated in this specific area, what is the environment, the larger scale environment impact on the polar low development. Because the polar low is closely linked to the cold air outbreak, and if the cold air outbreak is becomes stronger, and probably it will enhance the intensity of the polar low. But that's something that we want to investigate, but we haven't done yet, because here it's just a simple test. We assume that polar low in the future climate will also generate it here, exactly the location as the current climate.
Thank you, Lichuan. Any more questions from our in-person audience? No. Any questions from our Zoom audience? You can raise up your hand and unmute yourself and speak. Will, do you have a question?
Yeah. Thank you, Lichuan. Very nice. So a question is, so is the single biggest factor then the presence or absence of ice?
Sorry, I didn't get the point.
Is the single most important factor for the changes the presence or absence of sea ice?
So I would say that when the polar low closing to the ice age, the sea ice is probably the most important factor. But if the polar low generated it's a little bit far away from the sea ice, then that is the atmosphere stratification, and also the baroclinic instability is also linked to the atmosphere temperature profile. That will be more important than the sea ice. Definitely similar, linked to the previous question, the cold air outbreak here is close linked to the sea ice. Then if the cold air outbreak produced or generated moved a little bit north, then definitely the polar low will be, I would say that the polar low will also shift to the little bit north.
Okay. So second question. So you focused on 2 storms in your study. Did you look at all at whether the seasonality of the systems is going to change?
Yeah, the polar low is mainly happened during the winter time, and during the summertime, it's quite rare, and in the north hemisphere. But in the south hemisphere, the polar low even in the summertime can happen, but it's also quite rare. We didn't check because here we only checked for the 2 polar low cases. One is in December, one is in January. And I would say that they probably have seasonal pattern because the climate warming signal at different months, different season may a little bit different. That's something that we haven't done yet.
Okay, so you weren't looking at the initiation at all, but that's a completely different study as to whether or not you expect to see a delay in the onset of the storms, but possibly an extension of the season.
Yes, exactly.
Okay, interesting. Thank you.
Thank you.
Thank you, Will, for the question, Lichuan for the answer. Any more questions from in-person or Zoom audience? No? Well, let's give our speaker one more round of applause.
Thank you very much.
Thank you, Lichuan, for
Thanks,
coming.
Lichuan.
Thank you. Bye.
Our next talk will be Wednesday, 3 p.m. Eastern. I think our speaker will be Professor Amy Clements. So we'll be here on Wednesday. Thank you, guys. Happy weekend.